Have you ever stopped to think about how things flow? From the weather patterns that circle the globe to the actual blood moving through our veins, our entire world is run by these hidden rules of fluid dynamics. So today, we're going to pull back the curtain and look at some of the most surprising, totally counterintuitive secrets about how stuff moves. All right, let's just jump right in with a super simple question. Imagine you've got a ramp. You pour some water and some honey at the top. Which one wins the race to the bottom? Come on, it's obvious, right? It's got to be the water, no question. But what if I told you that's wrong? Well, sometimes. In 2020, researchers at Aalto University discovered that if you set things up just right, honey can flow 10 times faster than water. Yeah, you heard me, honey. It sounds completely impossible, I know, but it's true. And figuring out how that happens, well, that reveals something incredibly powerful about the physics of flow. So, to solve this little mystery, we have to understand what's actually happening inside any fluid that's moving. It's not just flowing along peacefully. There is a constant battle going on, a tug of war between two really fundamental forces. This whole battle really boils down to two key ideas. On one side, you have what are called inertial forces. That's basically the fluid's momentum. You can think of it as its stubbornness to keep going in the same direction. And on the other side, you have viscous forces. That's the fluid's internal friction, its stickiness. NASA has a great way of putting it. It's how heavy and gluey a fluid is. Obviously, honey is super viscous and water, not so much. So how on earth do we know which force is winning this tug of war at any given moment? For that, scientists use this beautiful, elegant, and incredibly powerful tool, the Reynolds number. It's just a simple number with no units, but it boils that whole complex battle down to a single value. It's basically the scoreboard for the fluid's internal fight. And what does that scoreboard tell us? It's pretty straightforward. When the Reynolds number is low, it means viscosity is winning. The flow is dominated by all that stickiness, which creates a smooth, predictable pattern we call laminar flow. Think of thick, lazy honey oozing from a jar. But when the Reynolds number is high, inertia takes over and the flow goes wild. It becomes chaotic, unpredictable, and turbulent, like a raging river. Now, let's see how this simple idea, this ratio, can be built into a tool that's so powerful it literally keeps our world running. You see, understanding this balance isn't just a fun thought experiment. It lets us engineer our world with unbelievable precision, using something called the Reynolds equation. This thing was first figured out by the man himself, Osborne Reynolds, way back in 1886, and it immediately became the absolute cornerstone of lubrication theory. It perfectly describes what happens in those unbelievably thin layers of fluid that separate moving parts and stop them from grinding themselves to dust. Whoa, okay? Don't worry about the math here. Seriously, you do not need to solve this. The only thing that matters is what this equation does. It lets engineers calculate the exact pressure inside a super thin film fluid, which tells them exactly how a lubricant is going to behave when it's squeezed between two moving surfaces. And its applications are, well, everywhere. This one equation is absolutely essential for designing everything from the tiny ball bearings in a skateboard to the critical dampers that keep a jet engine from shaking itself apart. It even helps us understand how the lubrication works inside our own hips and knees. It's literally the math that stops the world from squeaking to a halt. But what if you don't want to prevent friction? What if your goal is the exact opposite? What if you want to create controlled chaos, to mix things as efficiently as humanly possible? Well, for that, we have to switch gears, moving away from equations and into a totally different way of thinking, topology. This brings us to this amazing concept called topological chaos. And the basic idea is this. For really efficient mixing, the specific pattern of movement can be way more important than how fast or how hard you stir. It's about designing a perfect, choreographed dance for the fluid to follow. So here's the core idea. If you actually track the paths of some stirring rods as they move through a fluid over time, their paths create what mathematicians call a braid. And this braid isn't just a pretty pattern. It acts as a set of rules, a set of obstacles that forces the fluid to stretch, fold, and tangle up in a guaranteed, highly predictable way. And we can even measure how complex, how good that dance is. We use a value called topological entropy. A braid with a high topological entropy means you're guaranteed to get more stretching, more folding, and that means radically more efficient mixing. The whole game is to design a dance with the highest possible score. So let's see what this looks like in the real world. This device is called the silver mixer, and it's designed around these exact principles. At the very beginning, you can see we have two fluids, a gray one and a white one, and they're almost completely separate. Now watch what happens. As the rods start to move in a very specific choreographed pattern, a motion called the silver braid, which has a super high topological entropy, they don't just stir the fluid around. They literally grab it and stretch it into these incredibly long, thin filaments. And by doing that, they just massively increase the surface area between the two colors. And look at the result. It's a beautifully, almost perfectly mixed state. And this incredible efficiency didn't come from stirring faster or with more power. It came entirely from the geometry of the movement itself. It's a solution that was born not from brute force, but from a much deeper, more elegant understanding of patterns. So let's bring all of this together for a second. We've looked at how the hidden world of fluids can be understood through a simple ratio, a really complicated equation, and a beautiful, elegant pattern. First, we used the Reynolds number, that simple ratio, to predict if a flow was going to be smooth or totally chaotic. Then, we saw how the Reynolds equation lets us calculate pressure with incredible precision to solve real-world engineering problems like lubrication. And finally, we explored how these abstract patterns, these topological braids, can be used to design hyper-efficient mixing systems from the ground up. And here's the big takeaway. Mastering these hidden rules of flow is absolutely fundamental to our modern world. It's what lets us build more efficient machines, design better medical implants that work with our bodies, and create brand new ways to mix materials for everything from life-saving medicines to advanced manufacturing. Think about it, from the way cream swirls into your morning coffee to the vast invisible currents in the ocean and the atmosphere, these rules of flow are everywhere. And once you start looking for them, for that dance between inertia and viscosity, for the hidden patterns in the chaos, you start to see the world in a completely new light. The only question left is, where are you going to see them next?